search of our cosmic origins. Located high in the Andes mountain range, the 66 antennas that make up the Atacama large millimeter sub-millimeter array, ALMA, are an imposing sight. Under one sky, more than 20 countries embark upon a scientific endeavor that can only be realized through collaboration. North America, Europe, East Asia, and Chile work together to answer humankind's fundamental questions. Northern Chile was chosen as the site for ALMA because the Atacama Desert is the driest in the world. Its atmosphere, almost devoid of water vapor, enables detection of some of the faintest signals from the universe. Over 16,500 feet above sea level and covering distances of up to 10 miles of the Chajnantor Plateau, the Alma Antennas work as a single large telescope. A supercomputer combines and synchronizes all of their signals in real time. Thanks to this engineering and scientific feat, we're learning about the cold universe, the secrets of planet formation, and the chemical elements that constitute the building blocks of life. Professionals from around the world work for ALMA, pushing the limits of knowledge every day. In Chile, about 50 staff members are based in Santiago, while another 200 work in shifts at the Operations Support Facility close to the town of San Pedro de Atacama. Most of the staff works in the offices, laboratories, and antenna control room of this facility at an altitude of 9,500 feet. Others ascend to the Chajnantor Plateau at 16,500 feet to maintain and relocate the antennas, among other tasks. Strict safety protocols are crucial under these conditions. Thanks to leisure and residential facilities, staff can lead a healthy lifestyle, playing sports and games, watching movies, enjoying nutritious meals, and resting in comfort. ALMA plays a key role in global astronomical efforts. Along with other radio telescopes, it allowed the first image of a black hole to be captured. Without ALMA, that goal would have been unattainable. The Chilean astronomical community actively participates in ALMA research and discoveries, using its 10% of observing time. The radio telescope also contributes to workforce development and supports national and regional scientific, technological, and outreach projects. An example of the latter are the thousands of visitors who tour the facilities each year. ALMA respects the local Licanantay or Atacameño indigenous culture, supporting educational and other projects in the town of Toconao and San Pedro de Atacama, preserving archaeological heritage sites, and protecting the unique flora and fauna of the region, to name a few initiatives. Mirroring the antennas that work in unison with one goal, under the same sky, the international collaboration that ALMA embodies continues the search of our cosmic origins.
Hey everyone, good afternoon. Welcome to another virtual tour of ALMA. My name is Thais Mandiola. I'm a visitor coordinator at the observatory. Thank you so much for joining us today. And this special occasion, we will be talking about the Very Long Baseline Interferometer, the Vlvi. Really a mouthful that our guests will help us to unveil, okay? But before we start, and I see that there are some questions starting to come by to our platforms about this. It's important that we clarify that in this moment, and almost 2 years now, there are no visits to the observatory due to the pandemic. Hopefully, we will be opening for the visitors soon. So we will start introducing our guest today. We have Jeff Crew. He's one of the Event Horizon Telescope collaborators and MIT Haystack Observatory. He's a software engineer for the technology that is used to make this possible in Alma. Hi, Jeff. How are you?
Hi, Thais. Good to see you.
Good
Although
to see
virtually.
you. Yeah. It's great to have you here with us. We also have Hugo Messias. He's Alma Vlbi Observations Coordinator. Hola, Hugo. How are you?
Hi, everyone. Nice to see you all again virtually.
Yeah, great to have you both.
Directly from the control room.
David is also with us too, or he's not yet arrived? Yeah, here's David Rebolledo. He's an Alma Vlbi Observations Deputy. Hola, David. How are you?
Hello, everyone. Hello.
Hi.
I'm little Diego.
Hello, Diego. Welcome too. So thank you for sharing with us today. And about today's subject is the same technique that was used and which is very famous for the image of the shadow of a black hole, M87. And Vlbi does interferometry in a way that is similar to what ALMA does, but the telescopes are all over the world. So it's not possible to connect them together with optical fiber as ALMA does. Instead, they record the data to hard disk and ship these disks. With baselines of over 1,000 kilometers rather than kilometers that will be 16 in the case of ALMA, obtaining really 1,000 times better resolution and thus can probe deeper into the structure of astronomical objects which are bright in millimeter wavelength. The EHT collaboration that our guest will tell us about more during the talk is an alliance of 11 telescopes around the world, of which ALMA is the most sensitive element, joined together to create the virtual Earth-sized Event Horizon Telescope. So the EHT collaboration boasts more than 300 researchers from Africa, Asia, Europe, and South America. And about this information, we have a video that can explain a little bit more in general terms how all of this works. So if Nicolas can help me showing this video, that will explain more.
Imagine you see a friend carrying an invisible box and you want to know what's inside. The only way for you to guess would be to look at your friend's gestures, movements, and expressions. Difficult, isn't it? Astrophysicists have the same problem with some of the strangest objects in the universe, black holes. They want to understand these mysterious phenomena, but they have very little to work with. Imagine squeezing the entire Earth into a ball the size of a fingernail. Sounds a bit crazy, doesn't it? Well, that's exactly what scientists calculated black holes should be like decades ago. Physicists theorized that an object with an enormous density would have so much gravity that it would even capture light. But just like you can only get information about what's inside your friend's box through his movements, the first proof astronomers got that black holes really existed were their effects on nearby stars. Black holes have never been studied directly before because they were either too small or too far away. Something so far away is impossible to study with a single telescope on Earth because it would just not be powerful enough. Only a telescope with the size of the entire planet would be able to peer into a supermassive black hole in the center of a galaxy. This is why astronomers have decided to work together and create one. By simultaneously using 8 radio telescopes, including ALMA, distributed around the world, they achieved a level of detail equivalent to a single telescope the size of the Earth. All of this hard work just to obtain the first single image of these mysterious and strange objects in the cosmos.
Great. This is a great way to get into this theme today. And well, the first question that I want to make to each one of you is if you can tell us what are you doing during these days and what is exactly happening during this month. Jeff, if you want to answer.
Sure. We we have a campaign every year at about this time because it's a good time to look at the center of the galaxy and also M87, which you saw the picture of. And right now we just finished up the EHT run. That's the last 12 nights. And in the next 5 nights, we are going to be observing with the GMVA, which operates at slightly longer wavelengths. So we're all kind of catching our breath and cleaning up the logging of what we've just done and getting ready to do the next part.
Perfect. And you're talking us from?
I am at home up in Boston, Massachusetts.
Perfect. And are you coming for any of the observations, or it's going to be remotely?
No, the pandemic forced us all to learn how to operate telescopes remotely, it's funny, we've talked about doing that for years because it's a lot less wear and tear on the body to not have to go to high altitude.
Yeah.
And so it forced us to figure out how to do things remotely. And I would say it's mostly working. But I do miss the observatory, and I hope to be down later this year.
I can imagine, yeah. What about you, Hugo? Where are you talking us from? David. Just a second, he's working.
Yes, Hugo is now trying to get the system back. Yes, the last, as Jeff said, over the last few weeks, we have been working on all the technical details to run the observations. We have 2 projects, as Jeff said, that we have the EHT, which was finished last Saturday night. And the process started a few weeks ago when we get all the information from the people who create the schedule files that actually provides the details of observations, which sources are going to be observing which time. And we need to pass this information into the Alma system using software that Jeff and Hugo mainly developed. And we execute all this software to translate what is in the EHT world into the Alma technical system. So that's a preparation that we have to do. It's a preparation that takes some iteration because sometimes we find errors or sometimes we find some problems with the time that Alma can observe some sources. So we need to provide feedback to the developers to fix these problems and have everything ready. So that's more or less what is before the observations. And during the observations, we just run everything that we prepared before.
Perfect. Thank you so much. And well, before we start going through the bits and pieces of this subject that would allow for 1 hour, that is not much to go into this information, but we will try. If each one of you can tell us what is your role in Vlbi observations. You can start with you, David, maybe this time.
Yes, absolutely. I am a Vlbi friend, which is in Alma, which basically I am there to help with whatever Jeff and Hugo needs to be done to the preparation, from organizing internally in Alma the observations, making sure that everything is going to be available for us, talking to people internally in Alma if there's going to be, for example, engineering time or software time that can produce a clash in the time with given observations in the EHT or GMBA. So we need to coordinate inside, and also, as I said, coordinate and try the observations schedule files that are provided by the 2 groups, run through the Alma system and find mistakes and provide feedback. So that's more or less what I've been doing over the last few weeks. And during the observation, actually, I was the AOD and Alma, the astronomy on duty and in Alma last week. So I was helping with the observations as well, especially over the weekend.
Okay, perfect. How about you, Jeff? Tell us.
Yeah, so I am part of the Event Horizon Telescope, and I worked originally as the software architect for the Vlbi at Alma, which is to say I'm the guy who had to figure out what software needed to be written and what it had to talk to and a whole bunch of things, and then test it all And so that was how I started coming to Alma 10 years ago, was to figure out how to do this stuff. And I've been coming ever since as the EHT's representative to coordinate with the with Alma on observing schedules and time of observations, and a whole boatload of very boring logistical details like shipping all that media that we record on. Once we get done with the campaign, I get to return to Haystack, which is just down the road, and we get to do the Vlbi correlation, which I'm also involved in, where we try to actually take not just Alma's data, but the data from all the other observatories and figure out how to reduce it, and then produce the raw material that the scientists, the astronomers, use to make the image and other observables.
Amazing. So you started from the beginning of all of this.
Just about.
Yeah.
Yeah, I missed the proposal to all the people to get money, but
okay. And you, Hugo, can you help us with the answer?
Yes. So what I'm supposed to do here is what also David said. I mean, although I'm sort of the coordinator of the group. I've been mostly doing what David said. I mean, preparing the observations, trying to coordinate what are the possible possibility conflicts with whatever is the normal work, daily work with Alma, and that requires a bit of mind jiggling to actually understand when and which are the projects that can be run. So we provide suggestions. Doesn't mean that in the end it's the one that it's accepted, but we give our suggestions. We provide readiness, and I mean, in the future I will have to take over some of the things that Jeff mentioned also. So I'm learning since 2017. I'm learning a lot of Jeff, and he's a really nice person, and we are really lucky to have Jeff here with us, and I mean it's amazing. So
now I'm blushing, so you can be quiet.
No, definitely, it's great to have you, all of you, here to explain us that we're talking all the time with VLBI acronym. So maybe if you can explain what is really VLBI, how does it work? We saw a short video, but for people that are starting to watch us now, maybe it would be nice to have that explanation. Who will take the charge on that?
I'll give it a crack. So Alma is an interferometer where the dishes are all on the same plateau, as the video said. This is a movie that shows some of the EHT sites, and those yellow lines are the baselines which connect pairs of antennas. So for every pair of antennas, we make recordings at every antenna, and we take the information back to the correlator. We have two, one at Haystack and another one in Germany at Bonn. And if you analyze the signals on each baseline, you can compare them, and if you shift them in time, you find an exact time when the signals are the same. And if you're off in time, then they don't look like each other. But when you find exactly the right shift, you get a delay measurement. And that delay measurement has to do with when the light from the distant object, the black hole or anything really, arrived at the Earth. It sort of arrives as a plane. Think of a sheet of flat paper moving through the Earth, and it hits the near parts of the Earth first and the far parts of the Earth last. And so that's what we're trying to measure. And by collecting that information on a dozen telescopes, that's where we actually learn what's going on with the source. The tricky bit is that to do this, we need to record immense amounts of data. And at the end of the day, we get a handful of numbers out of it. So it's probably the most extreme example of taking lots of data and coming up with very small amounts of information.
Great. And what is it necessary, like, technically speaking, for this to work?
So what is recorded at all the sites, the telescopes, they're very expensive radios. So it's very much like listening to a radio, an ordinary radio in the audio, or even this this virtual tour. You can imagine playing a recording of this tour 10 minutes later, and what I'm saying now would correlate very well with what I'll say 10 minutes later in the recording. What we need is lots of bits to record all this information. And then we also need very precise timekeeping. Almost telescopes are all tuned to exactly the same frequency. And they can do that through a common frequency reference, which is we use a hydrogen maser that provides that signal. But at the other telescopes, they need to have a time standard that's as good. Otherwise, we end up tuned to slightly different frequencies and we don't correlate again. That would be like trying to compare this streaming session with some other unrelated streaming session. So we have to get all these details right, and we have to get them right to rather ridiculous precisions.
Very interesting. Anyone wants to add anything? Do you hear me well? I know that my sound is not very good.
It's a bit just it's good, but it's lower than the usual. Yes.
Okay, I'm gonna try fix it. So yeah, if anyone wants to add to that information,
if I may, just to simplify, I always give this example. The way interferometry works is with waves. I mean, it's light waves, but it's waves. So one way to have an analogy on our body is to use sound waves. It's different waves, but it's still, you'll be using the interferometry on your brain to actually, if you hear dogs barking, you'll be able to characterize where they are, their position, if they're big or not, what kind of dog it is. Maybe you can imagine. So your brain is trying to fit your experience, your life experience, to what the sound and what enters into your eardrums. And that's basically doing interferometry in your brain. So the antennas, instead of having two, we have, we can do this Vlbi thing at Alma with up to 50 something. I mean, and it's until 16 kilometers. But then the EHT and GMVA, they have much bigger baselines, and so that's it. I mean, the ears and the eardrums are different. But that's the best. Yes, that's the best analogy. That, I mean, if you haven't, I
have one baseline.
Yes, we have one baseline. With one baseline, you can characterize the dog. I mean, all that kind of thing. So basically, that's what Alma does. Other interferometers does, and of course the EHT. But again, the details that Jeff mentioned are amazing. I mean, the precision that we need we need to have to actually be able to do this at such thousands of kilometers. It's amazing. And technologically wise, I mean, it's amazing that we are alive and watching this happening. So yeah.
Definitely. Yes. Thank you for sharing that information. I have another question about the capabilities of Vlvi. So which kind of objects is capable Vlvi to observe besides black holes?
Well, it's a little bit like asking what can you see. I mean, if you're in a dark room and there's no source of light, you don't see anything. So we are using radio waves because that's the only people are trying to do interferometry at higher frequencies, but so far radio waves is the only place you can do it. So you need an object that emits radio waves and emits enough of them so that it's bright enough to collect this information. So black holes are certainly an easy case because they're extremely bright and extremely powerful engines. We can see We now believe that at the center of every galaxy, there's a black hole making energy in the radio that we can see. And we can see galaxies throughout the entire universe, throughout the entire history of time. So that's kind of mind-blowing. We can't take close-up pictures of the black holes, but we see the radiation coming out of them. But ordinary astrophysical objects such as stars generate a fair amount of radio waves. Certainly the nearby stars are easy to see. There are, we mentioned a hydrogen maser that we use to keep time. A maser is well, it's like a laser. If you've played laser tag, it makes a great little spot of light somewhere. But maser is just doing that in microwaves, and it makes masers make very powerful radio signals. There are some stars where the conditions are just right in their atmospheres to generate maser lines at particular frequencies that we can pick up, and they're extremely bright. And you know exactly what they are because they show up at a characteristic frequency. So we can use that to gain information about stellar evolution. Molecular clouds generate radio waves. I mean, it's just the list is actually rather endless. We know that in molecular clouds, there are actually some fairly complex molecules floating around out there. Even, you know, alcohols, ethyl alcohol is found floating around in space. And we can tell that from looking at the lines of these moleculars. When they get hot, they emit at particular frequencies, and you can see that too.
Great. I have some video of the zoom in of the EHT. So in relation to that, if you can tell us a little bit more about the Event Horizon Telescope and how it relates with the Vlvi and what you're doing, the collaboration.
Sure. This video is the one that was made when we released the image. The M87 galaxy is at the heart of a nearby cluster of galaxies. It's the biggest and brightest galaxy in the cluster, and it has this jet of emission, which was how it was first identified almost a century ago. So people knew something was happening. And now we've zoomed in on it and actually taken the picture of the black hole. So the Event Horizon Telescope was built specifically to look at this object and also the one at the center of our galaxy. The resolution we can see with is determined by the spacing of the telescopes. So it turns out that the size of the Earth and the frequencies we're working with is exactly right to image this object and Sagittarius A star, which is at the center of our galaxy. So the Event Horizon Telescope was built specifically to go after these two objects and try to catch a picture like this. And then once we have the picture, to understand more about it. The main feature, you know, it's a donut, but the main feature is it's dim in the middle, and that is predicted by Einstein's theory when you do the math. The fact that it is brighter on one side than the other is actually connected up with the physics of what this object is doing. That jet of bright radiation in the optical that you saw in the movie is somehow mapped into this black hole image. And the tricky part is that because black holes are strong, have gravity strong enough to bend light, it's very much like going to a fun house with funny mirrors. And light goes in all directions and things are distorted and you have to untangle all of that. So we're working on it and we are learning things. It's not by any means a quick and easy study.
No, it's not. That's a great example about the distortion of mirrors. Yeah. David, would you help us going a bit through the experience that was observing this black hole?
Well, I wasn't in 2017, so probably Hugo can provide more insights, but I guess it's more or less what happening right now. You just, before the pandemic, we have to go to the OSF, as Jeff said, and we were all together a few days before to get everything done. unprepared. And when the observations happens, we were all in the control room looking at the results and seeing that the phasing of the antennas, which is the technique that we use to get all the antennas correlated, were working. And I don't know, probably we can say how was the experience of observing in 2017 when
Yes,
actually
please.
the data was taken.
Yeah, please.
I mean, it's I guess the experience was that, but it was also like, okay, this is happening, right? Yeah, because I remember the first time I came to Chile, I went to Concepcion, and there I was working with Neil Nagar, that actually then came to install the went to install the maser with a postdoc, right, Jeff? I think it was
Yeah, it was in 2014.
Yes. So, but before that, I remember coming with Neil to a meeting here at Alma, and at that time, I didn't think that I would end up as an astronomer here at the observatory. I dreamed about it, but, of course. I mean, but then the thing was. Then we met here with Shep Dolman, that was trying to also convince people that this was the way to go. I mean, what we needed to actually do to, and what were the impacts, not just M87 and Sagittarius A, but some, I mean, other science topics, right? And then at that time I got into contact through Neil also with this project, and then in 2017 when I actually got the chance to work with Jeff and also Violetta Pellizzeri, that was actually I took over from her and she went to Netherlands. So at the time the feeling was, well, that's a lot of information. It's cool to be here, but that's a lot of information. So I took my time to actually do as many questions as I could and as I could do and absorb. So because I mean, as Jeff already mentioned, it's quite a complex system, but it was really fun because it was very dynamic. I mean, the way things operate also changed slightly since then. So again, I mean, David probably also had this kind of experience when he joined the years after. But yeah, I mean, it was amazing, basically. I mean, if you want a word for that.
If I could make one comment, one of the things about this business is, these days cameras are digital, so you take a picture and you know what you took a picture of, and if it's not good, you just take it again. VLBI is a lot more like old photography, where you took the picture onto film and you really didn't know what you had in the camera until you took the film back home and developed it. And so, well, the whole time we're doing this, we're taking data and we think the data is good, but we have no idea if it's going to work or not until it's all correlated. So it's very stressful in that respect.
Yeah, definitely. I've heard stories, well, about how from the different stations in the world, you wouldn't know what would be the turnout of this picture. And when you compare it with the results of each one, it really was the same. So you could, so that's, yeah, we can explain a little bit more of that process. Did you understand?
As we showed in the movie, the analysis of the correlation process proceeds by baseline, and the measurements you get on a baseline, the delay and the strength of the signal, comes out of the information from the pair of stations on that baseline. Now, the number of baselines, as you add more stations, every station you add generates a baseline to every other station. So the EHT in 2017 really, and if two antennas are next to each other, they're seeing the same thing. So we really only had 6 locations on the Earth providing information, which is not a lot. In this last campaign, we've added 3 new stations relative to 2017. So we're up to 11 stations. So the number of baselines is 66, I think, which is many times the amount of information that we had when we took the first image. Now, you can go through the process of making the image is fairly complicated, but once you have a model of what the object looks like and you can fit it with this data, you can take stations out and see if the image changes. And we do lots of experiments like that to be sure we really have the right image. And one of the things that was astounding to us about the M87 image is that you get it from very few baselines once you've figured out what it is. It's very robust. And the details of that are hard to explain, but there's absolutely no question this is what the thing looks like. Now, this is a simulation of the black hole in the center with an accretion disk of hot gas swirling around, and going up the top of the figure and out the bottom is gas that has been heated and streaming out along magnetic field lines. And we're rotating this image very slowly so that we're actually going to be looking down the barrel of the jet. So how the image looks depends a lot on the look angle. Here we're looking right down on it through the jet, and we see the gas streaming around. The black hole's pulling it all in, so it's like flushing a toilet. And of course, the black hole itself eats all the light that goes near it, which is why it's black.
Great. Thank you for that explanation. And how was the experience for each one of you when this image was published?
Oh, I can start. I remember we were at the OSF the week before. There was this big announcement. If you remember, Jeff, we were up the hill, and there was a total embargo of having anything extra besides that's going to be a big release news. And I was at OSF with Jeff. Jeff, what's going on? What's going to happen? And Jeff said, wait until next week, and you will know. So it was an exciting moment. We were at the OSF doing Vlbi stuff, but yes, for me it was a one experience. And after that, I saw the news. I saw the press release and all the each part in the world telling about this amazing image was quite. I was lucky to be there and slightly be part of that. Even I didn't participate in the 2017 campaign. I felt that something big was going on around me, so that was a good experience.
Great. What about you, Hugo?
This was during the day. Actually, it was fun because you'll see. I got lucky because I was sent the draft a little bit before, and when I saw the image, I said, "Wow! The cool thing about this is that it really looks like a simulation." But I know that they are not like lying to us, right? Because I was there observing, and so it was like, yeah, we made it. I mean, you felt part of the team, or part of the effort. I mean, when the thing is, this is one of the things that when you reach the end of your generation, you say, yeah, I was the first kind of not generation, but group of people on Earth that actually managed to see the shadow of a black hole, and no one will take that away from me. I mean, that's a big tick in your lifetime, right? But the other tick is you were part of it. I mean, I feel like I was there at the right time. I involved. I asked to be involved in the Vlbi observations. People said yes, go ahead, and I contributed. And I did my best. And if it wasn't I being the fellow that came here selected from the committee at the time, it will be another person. So I really feel like when I saw that image, I really felt lucky for the opportunity that I was given by being here, and I felt useful because I contributed to that thing. So it was pretty cool. As for the media, I was not expecting. I mean, these things normally last for 3 days, the enthusiasm, maybe a week. But these, I mean, these went on for months and months. So that was, I mean, just because we had an image. I mean, you didn't see this impact also on the gravitational waves results. Even though the gravitational waves, it's something, it's a whole new way of observing the universe, also related to black holes. But the impact was not as big as this one because, I mean, there was an image for people to see.
Yeah, definitely a historic moment. And after 10 years of being really working hard on that, how was it for you, Jeff, to have that finally that image?
I was just surprised it all worked. I mean, to be honest, you spend a lot of, I've worked on a number of things over my life, and you know, I spent 10 years on this, 15 years on a satellite, and the first 5 years went up when the rocket failed. So that didn't work. But this was, you know, well, it's been 10 years of my life now on this thing, and it all seems to be working. And to me, that's the most amazing part, is that you can figure out how to build something like this and have it actually work. But, you know, moving beyond that, I really was not prepared for how interested everybody on the planet seemed to find this interesting. And I think that's really cool and a really important statement about us as human beings. I know it sounds a little sappy, but we live in a fantastic universe. And this is a great time to be alive, because there are all these age-old questions that we're starting to pick apart one by one. And finding the answers to these questions, you know, doesn't end the story. There's even more to be understood. It all gets to be much more interesting than you ever thought it would be. And, you know, I could go on for hours on that topic. But, you know, this is, I mean, Einstein came up with these equations over a century ago. And now we still don't actually have all the theories of gravity sorted out. We just have this nice picture which tells us that, yeah, we understand the bending of light and gravity and things that Einstein would have understood. And he's, you know, it's another confirmation of his theory. But there's so much more going on. You know, and the thing about black holes is they eat all the light that's near them, and they don't tell you very much about them. As objects in Einstein's theory, we know how much we can know their mass because of how everything gets pulled in. We can even tell if they're spinning because that has some effects on the way things get pulled in. Black holes can actually be charged the way ordinary static electricity. You could charge up a black hole and electrical things would get pulled into it. But that's about it. And, you know, that's not enough to answer any of the quantum mechanical questions about black holes. There's all kinds of and people are still puzzling about all of those things. There are many paradoxes and curiosity questions associated with black holes, which would, again, be a topic for another lecture. So there's a long way to go, and it's just really cool. You know, when I was a kid, you know, galaxies they didn't even know what they were half the time. It was just some shiny thing. And then people figured out, yeah, there's lots of galaxies like ours. And now we know that, well, you know, why are there galaxies here and not there? And it's like, well, because there's black holes at the center of every single one, it seems. That's really cool.
That's really cool, yes. So let me read some of the comments that we have on our stream, because we're streaming for Twitter, for YouTube. So we have people from Buenos Aires saying hi. We have from Italy too, so we can, yeah, greet them. Let's see if I have a question over here. Nikos says, lovely kid, future scientist, for Diego there. There's a big question here that is asking about mathematically about correlating different types of telescope, perhaps optical and radio telescope. What do you need to know mathematically? That's the question, to correlate the different telescopes.
So correlation is a fancy word, but it basically is saying this thing is like this other thing. And everybody can do a very simple experiment. Take an ordinary coin and flip it, heads and tails. Heads and tails. Just write it down: heads, tails, heads, heads, tails, tails. And you can have two people doing that at the same time, and they're going to generate. If the coins are fair, they're going to generate different sequences of heads and tails. But if Thais comes along to two people doing that and tells each one, "Hey, I want you to make this one heads, or I want you to make that one tails," and she does it, she coordinates how she tells them, then if you take their lists and line them up, you will be able to shift the lists back and forth and find the moment where they actually agree. That's correlation. So the thing about radio waves is that we can take the signals from the telescope, excuse me, we can convert them to digital signals, and we can do all this calculation in the supercomputer of Alma's correlator, or the one we use for Vlbi, and make that measurement. If you can't digitize it, and that's true for the higher frequencies, if you go into optical, it's the signals, the frequencies are so high that you cannot usefully digitize that information. You can still make interferometry work by basically with mirrors and lenses and stuff. You can get the two signals to interfere, and you can do some interferometry that way. That's how gravity works, and people are working on that. And it carries all the way up the radio spectrum, to X-rays and gamma rays, and those are even harder. But with the march of technology and clever people, we will someday figure out how to do those sorts of things, because it's all light and the same physics applies. And that will mean that we can reach deeper into some of these objects. I hope that answers your question.
Thank you. David Fernandez is asking, what are the next steps for the EHT?
Well, more telescopes. More telescopes. We're working on one in California. We're working on one in Namibia. There's one just over the Andes called Llama, which is a joint South American project. And as I said, every telescope you add adds n times as much information. So each additional telescope adds a lot more information. So number one, we're looking to build more telescopes just to increase the ability to make better images. The second thing to go is to go off into space. We can't make the Earth any bigger, but if we can put one of these just one telescope in space, then we can get longer baselines, which increases our resolution. My personal dream would be to take the whole array and put the whole thing in space. And then the sky's the limit. We can really get any resolution we want. And our only limitation is how bright these things are. That'll take a few years to figure out, but it will come.
It will come, yeah. And we have Oscar Mauricio Cepeda is asking, what determines the spin direction of a black hole vortex?
Luck. It's born at some point. And, if you take a ball and throw it in the air, it's very hard actually to throw a ball that doesn't spin. But the spin of a ball that you throw in the air comes from how you release it and the initial conditions. And then once it's spinning, it stays spinning. So the spin of the black hole is really an imprint of how it was born, what gases collapsed on it. In the movies that you've seen, there's typically an accretion disk. So if you have some gas and you put a central mass on it, it tends to collapse first into a disk and rotate, and then it falls in. So it's the rotation of that disk that actually drives the black hole spin.
Great. So we have another answer for the audience. I don't see any other questions from the chat.
I would also add that the cool thing about the black hole sometimes is that they seem not to care how the galaxy is rotating. I mean, you can pierce through the core of the galaxy, and whatever the black hole is doing is nothing related sometimes to what the galaxy is doing. So that's why sometimes you see these really crazy images of the jets going out of the galaxy, and it's not oriented perpendicular to the galaxy. And when Jeff previously was talking about why are some galaxies grow so big and others don't, or why why galaxy population seems to reach a limit, and one of the things are these jets. I mean, if these jets actually manage to interact with the gas that would eventually become stars or turn into stars, either because it steered it too much so it won't collapse into stars, or because it pushed out of the galaxy so it's not dense enough then to collapse. So it prevents the conditions for stars to be born. These are the jets. And if you see a really big jet, it means that actually the black hole is rotating in the same direction as the accretion disk that Jeff was talking about. I mean, one of the things. Oh, I'm seeing a bunny here in Santiago. Sorry, I got distracted. So if you actually, one of the things about these observations was that the image itself did not tell the whole story. So that thing with the bright spot in the south is actually telling that the gas is rotating. It doesn't tell us if the black hole is also rotating in the same direction or the opposite direction. So, but models, and again, models are limited to our knowledge or what we think of that is happening, but to our knowledge, if we have the jet that we see in M87, it also means that the black hole is actually co-rotating with the gas. If it was the opposite, then the models or the way we think the universe behaves at these scales and these extreme gravity conditions will not produce that jet. So it's cool. I mean, it's historically we've been studying. I mean, just the community has been studying the jet in M87. Actually, in month scale, it has seen it moving. I mean, I invite everyone to actually search for these images. It's amazing, and based on that information helped the team to actually say, okay, yes, this thing is co-rotating, and so the system is rotating this way.
Great, thank you, Hugo. And we received some questions from Instagram because we left a box of questions before the talk. And one of the questions that is very frequent about this is, what is inside of a black hole? And if it's possible that the black hole absorbs the Milky Way.
You can fill a black hole with whatever you want. Nobody can tell you that you're wrong. If you want to fill it with puppies, go right ahead. All we know about it is the mass. We don't know how it's distributed. We don't know what it is. And actually, the cool thing about supermassive black holes is that they're so large that they have a lot of space to store all that mass. So you actually, if you had enough Beanie Babies, you could make a black hole out of them, and so, yeah. So there's really no way to know. All we know is what the gravity of the thing is, and you could fill it as it gets bigger and bigger. You could fill it with ordinary water, and that would be good enough. Now, how did you make it in the first place? Well, the only way we know how to make black holes is through gravitational collapse of very heavy stars. And those go through a stage called a neutron star, which is like a super big atomic nucleus, but with the mass of a sun. And if you add more and more mass, the nuclear forces that keep the neutron star together are overwhelmed by gravity, and then it collapses. And we don't know of any force that can withstand that collapse. And that's why it's a black hole and it has no light. And we really don't know. Nobody actually knows the answer to that question. Which, again, as I said, don't be discouraged, kids. There's just no limit to the things that we need to figure out. And that's why you study hard. And, you'll get a chance to do some of this stuff someday. Yeah, I just can't tell you what questions you get to answer.
And how about, because you already answered what is coming for EHT, more telescopes, more stations, but in the case of science and the discoveries, if you can give us a clue of what direction is taking this researches and walk us through about that. If you can tell anything, or is confidential?
No, well, as I said, every galaxy has a black hole. So this most recent campaign. We can't talk about it yet because we haven't even analyzed the data. But we've looked at some new objects that have been on our list to look at for years, and we now understand how to operate the array to observe fainter objects. So our discovery space of objects that we have looked at has grown considerably. Within the last year, we've added a capability. I mentioned earlier the spectral lines from masers, stellar masers. We actually now know how to make observations of those, and those are actually offered for the current cycle of observing. So if people want to learn more about that and put together proposals to look at some of these objects, those are completely new observations. And again, we're bringing the sensitivity of ALMA to these things. So people have looked at these objects before, but there's a limit to what you can do. And you're usually limited by how bright it is and how much noise there is. But ALMA is so sensitive that we can take fabulous data and we'll learn more about these things. And these spectral lines are all about molecules and the building blocks of life. And that's what ALMA is all about. It is mind-blowing to me what ALMA has discovered in the past 10 years. We know more about distant galaxies, molecular lines, and so forth than we knew before ALMA was built. And as I said, it just gets better and better.
Thank you so much. So we'll be finishing now our tour. I don't know if you want to have a few words just to finish and to the people that are watching. And I really want to thank for each one of you participating today. And I'll leave you to the final words. Thank you so much. If anyone wants to say goodbye to the audience.
I want to thank Diego for
Diego, yes.
Yeah. The nice side of the pandemic is I get to see the little kids of everybody. So thank you all. This has been fun. I hope I've answered your questions.
You have. Thank you so much, Jeff. Hope to see you soon.
Yeah, thank you. Thank you for letting us participating on this project. Thank you, Jeff, for the support, and we will continue supporting Vlbi as far as we can. So this is exciting times for science.
Yeah, for sure. Thank you for considering us on this activity. It's always good to actually try our best to actually show how things are done, like here from the control room, and give you everyone this sneak peek to actually the activities that we do for our own curiosity, so our and yours. So thank you for doing this activity. I mean, yeah.
Now go back to work.
Yes.
Yeah.
Doing my best.
We have the Spanish version in a few minutes. Okay. Ciao, ciao.
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 Thank you.